My name is Quinn Porteous, and this is my research and development project for 2021, Recycled Materials in Concrete. First, let's start off with the problem. Concrete is one of the most costliest materials when it comes to negatively affecting the environment, where the production of cement produces around 8% of the world's CO2 emissions globally. The use of silica sands from natural riverbeds is running out due to its necessity in both concrete and mortar for its alkali-silica reaction, and large aggregates are quarried from all over the world, such as limestone and granite, to be used in concrete. Something needs to change, especially when the world is wanting to become carbon neutral by around 2050. Thus, the goal is to find a suitable partial replacement for a component of concrete or mortar that does at least two of three things: reduce CO2 emissions, reduce waste sent to landfill, or reduce the use of natural resources, thereby reducing its environmental footprint and promoting a more sustainable future for the construction industry. To get a good idea of what's already out there around this topic, a literature review was conducted, and this is what was found. Recycling materials into concrete is something that has been done for over 100 years, and there is a lot of literature around this idea, starting from around 1910, where V.B. Swamy and G.N. Sheet investigated into the use of replacing sand with silica sand and artificial sand. Since then, there has been great strides in this area of research, where all sorts of materials have been tried and tested, such as using recycling concrete as large aggregates back into new concrete constructions, and recycling glass bottles as sand replacements. However, a material that lacks research is the use of sandblasting sand as a replacement for regular sand. But since this material is not of a large aggregate, there is no need to test concrete at all, and making mortar instead will be enough to test the properties and determine if this material has the capability to make it stronger. Thus, the focus of this research and development project: recycling sandblasting sand and mortar. Along with the sandblasting sand as a partial replacement for sand, fly ash was also used. This was to not only reuse a material that would otherwise be sent to landfill, but to also reduce the CO2 emissions of cement production. First, a water to cement to sand ratio was chosen of 0.613. This was chosen after testing with a ratio of 0.513. The mix was dry and resulted in a grainy mortar sample. Below is a table showing the batches chosen to be tested. Note here that the sand 10 means that the sandblasting sand is replacing the aggregate sand at 10%, while also it can be seen that the total amount of sand in the batch will not change. So this can be seen on 10, 20, and 30, how the total weight of the sample does not change. 3 tests were completed for each batch: compression testing, tensile testing, and flowability. These were to measure the mortar's reaction to the different mixtures of sandblasting sand and fly ash to determine whether the addition of these materials would increase or decrease certain features of the batches. Some of those results can be seen on the results section to the right of the poster over here. In both tests, it can be seen that the addition of fly ash has decreased both the tensile and compressive strength of the mortar. However, this was expected, as the main reason for using fly ash in the first place was to reduce the mortar's environmental impact on the planet. The sandblasting sand had positive effects on the compressive strength at 20% and greater, but in terms of tensile, this wasn't until 30%, and that could be seen here with the yellow line. The most important of results, however, is the combination of the two materials, where in compressive strength, the addition of these two materials actually increased the mortar's compressive strength at 10% replacement, peaking at around 20 and falling down at 30. Whereas in terms of tensile strength, the combination followed the same sort of path as the individual replacement tests, but gave better results at all replacement levels comparing to those individual tests exceeding the control strength at 30% replacement. Based on these results, if using 30% replacement of both fly ash and sandblasting sand, the use of this concrete is endless, as it increases both the tensile and compressive strength of the concrete. However, this is just in mortar, and further testing would be required to see how these materials would affect the batches as concrete as well. As promising as these results are, the availability of waste sandblasting sand is pretty low. So building large constructions wouldn't be possible, as acquiring that much sandblasting sand just wouldn't really be feasible. Additionally, COVID-19 had quite the effect on the testing period of this project, leading to no 7-day testing results, as the batches were completed before lockdown. But due to the NZ lockdown of the Delta variant, there was little to no access to the labs, meaning that by the time restrictions were lowered, it wasn't possible to complete additional tests such as the water absorption test. However, the results for compressive and tensile strength are relatively promising and could prove beneficial. This concludes my presentation on recycled materials and concrete. Thanks for listening.